and then go straight with. We start from last class. I go share. You got this screen? Can you see
Yes,
that?
sir.
Okay. Now we were discussing this. Okay. We were discussing the different molecular orbitals that was there that is formed from this. I think I'll just straightway quickly what we have done. For pi bonded system, only one pi bond. We have got pi and pi star formed from P1, P2. And this is for carbon-carbon single bond and double bond. Conjugated system for diene, it will be, there will be 4 pi orbitals which are formed like this. And then we have got this orbital picture will be like this: psi 1, psi 2, psi 3, psi 4. I think you have understood this. And you see here, which one is your HOMO? HOMO is your psi 2, and psi 2 is this one. So this HOMO and LUMO, these are the wave function that will be important for our discussion. Then we can triene, conjugated triene. So 6 pi molecular orbital, and 6 pi molecular orbital will be psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. And their orbital picture will be like this: first one no node, second one node, third one 2 node, then 3 node, then 4 node, then 5 node. And all nodes will be equally, equivalent way they will be distributed. So here there is no, here there is one node. So these 3 will have one phase and other 3 will have opposite phase. Then here we have got one node and 2 node, because these nodes also will be equally, will be distributed in equivalent proportion. So here no node in between, so same phase, but again there is a node, that means wave will invert. So there will be another opposite phase, then again nodes, so there will be another opposite phase. And here 3 nodes, 1, 2, 3, you see these changes. That is. And what is HOMO? HOMO is your psi 3. So you have to remember. And also you see in this psi 3, your terminal lobes are psi 3, terminal lobes are symmetrical. That means this one and this one, because these lobes will be important for our for that bond formation, because it is forming that cyclic bond here. So these two bonds will, these two orbitals will be, and you see here symmetrical. But when we see in this case, what is HOMO? HOMO is psi 2, and psi 2 here, this terminal carbon atom has got asymmetric lobes. You see here asymmetric orbitals. You see here, this is this phase, and this is the opposite phase here. So these things will be requiring. Okay. Now we come to this is we start here today. This was not there last class. We did not do this. Photochemical excitation in carbon-carbon double bond and conjugated poly. That means it is the pi-pi transition that we are talking of. Now, when we give energy in the photochemical, apply energy, and how much of energy is required, we have also shown it, because the energy that will depend on this energy gap between the HOMO and LUMO. And for this one, when this if we apply energy to this one, electromagnetic radiation, then this one electron will jump to the next orbital, which is vacant. So, so that becomes the excited state of the molecule. But in this excited, in the process, what has happened? In the ground state, HOMO was your pi orbital, but in this excited state, HOMO is your pi star orbital. And what is their orbital picture here? You see here, pi was having these two lobes side by side, same phase, but here pi star has got this opposite phase. So this is what you have to remember. Coming to now conjugated system, we have got, sorry, conjugated system. Ground state, we have got Psi1, Psi2, Psi3, Psi4. And the Psi2 was the HOMO. But if you excite it, if you subject it to electromagnetic radiation, then this electron will jump to the next higher orbital, that is Psi3. But in the process, in the excited state, what happens? Psi3 becomes now HOMO. Psi3 becomes HOMO. And you see the picture now. In Psi2, it is this one. The terminal lobes were antisymmetric, but in Psi3, the terminal lobes are symmetric. This is what is required. We don't require everything to remember, and it is very simple to remember also. It is not at all difficult. I think if you do practice at home, it will be done very easy. So this is, then when we go to similar thing, when we go to triene system, ground state, it is Psi1, Psi2, Psi3, HOMO is Psi3, LUMO is Psi4. But in the excited state, when we subject it to electromagnetic radiation, expose it to electromagnetic radiation, then this electron jump from Psi3 to Psi4. So Psi4, it will be occupied orbital now. And because of this, HOMO becomes Psi4 and LUMO becomes Psi5. So that is what you have to remember. Now here again, Psi3, you see, Psi3 was this one. The terminal lobes are symmetric, but Psi4, the terminal lobes are antisymmetric. So these things you have to remember. You got the idea? Hello? Just tell me, is it okay? I'll be sending this material to you after we complete these classes. Written document will be there, but you should also note down the points which are being told, because every time, of course, I am also sending my video lecture, but video lecture, I find the last lecture hardly anybody has seen. Some 13 or 14 people have seen it. Other people, they didn't bother to see it. That is visible to me. How many of you have checked? Let us go to the next part. Now, actual pericyclic reaction, the theory of pericyclic reaction. What is the, that is first one we are talking, electrocyclic reaction, theory of electrocyclic reaction. It is FMO theory, frontier molecular orbital approach. Frontier molecular orbital. Frontier means what? What is the meaning of frontier? What is the meaning of frontier? English meaning. Frontier means what? Now, in terms of geography, if we say frontier state, which is, what do you mean by frontier state for India with respect to India? Frontier means border state. All the border states, say Arunachal is the frontier state. Then your that way Jammu Kashmir is frontier state. Rajasthan is a frontier state. That means the outside, just outside that border, just outside. That means this UP. Okay, UP also you can say frontier state, but Madhya Pradesh is not. Maharashtra is not, because the other one is sea. Sea has got no, that is nobody's property. Frontier means outside. That means from here itself, the frontier orbital. What is the frontier orbital? That means the HOMO. That is the outermost orbital where these electrons are present. Is the HOMO. But HOMO, again, we have seen in ground state, HOMO is one. In excited state, HOMO is different. So what is the theory? In electrocyclic reaction are brought about by heat or light. You see here, heat means electric ground state, and light means charming. See, Marak, you put your sound mute. Heat or light That means that molecule in the ground state or molecule in the excited state are concerted, means simultaneously it happening, and stereospecific. Very much stereospecific. You understand the meaning of stereo. Now here is it is the HOMO of the reactant that is involved in the reaction. That is the frontier orbital. All right. The very approach theory of this one is that HOMO is involved. And where in phase overlap, that means when a bond is formed between the two orbital, the same phase orbital must come together. If they are of opposite phase, then there is no bonding. If the phases are same, same phase, if they come together, then the bonding is going to form. That is the simple theory. Then, so here again written, a symmetry allowed pathway requires in-phase overlap. In-phase overlap, that means overlapping in the same phase. Then we come here. These are two terms that you will find here: conrotation and disrotation. Conrotatory and disrotatory. Conrotation means we rotate this. We rotate the orbitals in two modes. One is called disrotatory motion, disrotatory, and another one is conrotatory. Disrotation means if one orbital we rotate in this direction, the other one will be rotated in the opposite direction. One in clockwise, other one anti-clockwise. So this one we call it disrotatory motion. In short, this. And conrotatory motion means if I rotate this one, suppose clockwise, the other one also needs to be clockwise. Or if this is anti-clockwise, this one also should be anti-clockwise. So that one is called conrotatory motion, in short called conrotation. And this is disrotation. So we have got two types of rotation, disrotation and conrotation. And of which one? It is the terminal orbital, because when we see when we see this bonding has formed, suppose bonding. This one, when we see where the bonding has taken place, this orbital and this orbital are involved. So it is this where the new sigma bond, this is the new sigma bond is formed, and we get this pi bond here. So when this new bond is formed, the orbital here, which is here, and orbital here in the terminal orbital must come together in such a way that they are in the same phase. So rotation of this orbital has to take place in such a way that they are in the same phase. Now, when they will come in same phase, the symmetry allowed pathway requires in-phase overlap. That means for bond formation, they must come together. Now, because it is HOMO which is involved, the HOMO in the HOMO, that end orbital may be symmetric or maybe antisymmetric. If it is symmetric, what happens? This lobe and this lobe will be having same phase. This lobe and this lobe having same phase. So for their bond, how they have to come? It has to come this way, and this has to come this way. So the rotation has to be this rotation, you see here. The rotation has to be this rotation. Also, not that I am giving here. It may be this way also. It may be this way also. This one and this. This also. If it is this way, then this will come like this. This will be they will come like this. So here also they are on the same phase. So not that only this way and this way. It can be also this way and this way. That means two of them are either one if it is clockwise, other one will be this is clockwise, this is anti-clockwise, and this may be anti-clockwise, this will be clockwise. So both way it is, any one of this one is uh, which will give this same phase overlapping, that is going to form a bond. So this one becomes, so what it is, so when it is, just listen here, when it is, when it is terminal lobes are symmetric, the rotation has to be this rotation to achieve the phase. And when it is homo is anti-symmetric, that means one is this way, other one is this one. Then for bonding, we must have con rotation. You see here, this con rotation will make it, if it move this way, it will, oh, sorry. My picture is, this picture is wrong. This picture is wrong because it is anti-symmetric, no? This picture is wrong, so this is wrong. So here we can check it. Con rotation, this one, if it is coming this way, this one will be this way. So what it becomes? This is the same phase. This is another phase. So they will come together. Got my point? Hello, this is wrong. I'll change it. And if you can do it this way also. In that case, they are connected to one another. So this is also all right. I think you got my point. Hello. Yes or no?
Yes, sir.
Okay.
Yes, sir.
Okay. All right. So next we go, guys. Now selection rule. Come to selection rule. You see, there are so many options. What we have seen that when there is the stereospecificity depends on what? Depends on whether the reaction is taking place under thermal condition or photochemical condition, and also what is the number of pi bond. Pi bond is odd number of pi bond or even number of pi bond. So all this. So Hoffman and Woodward and Hoffman had given this rule. So let us see what it is. It comes like this. It comes like this. Just see the chart. Number of pi bond. It may be even or it may be odd. If number of pi bond is even and odd, if it is even, that can be given by this formula 4n. If it is odd, 4n plus 2, where n is an integer. Even means 4n. If n has to be from 1, 2, 3, etc. So n minimum should be 1. So if it is 1, so it becomes 4 electron. If it is 1 here, and odd number will be 6 electron. That is the first odd electron number. 6 pi electrons. So we can also check it in terms of number of pi bonds. One is even or it can be odd. Then under when it is thermal condition, the HOMO becomes anti-symmetric, and the rotation is con rotation. We have seen this one, why it is con rotation. And if it is photochemical, HOMO is symmetric, and it becomes this rotation. And when we go to odd number, they just change. Thermal, symmetric, this rotation, photochemical, anti-symmetric, con rotation. Now, can you remember this? Under what? When you will be, that means Only two things. One is that is the rotation of the terminal orbital. Rotation of the terminal orbital that is required of the HOMO. We have to know HOMO is which one and see what is the rotation. Rotation can be, if it is symmetric, we will have, if it is symmetric, this rotation. If it is anti-symmetric, it should be conrotation. Now, can you remember how to when it is going to, without looking into the chart? Hmm? Without looking the chart, can you say when it is going to be conrotation and when it is going to be this rotation? Hello, tell me. Can you manage?
Yes, sir.
Huh?
Yes, sir.
How? Give us a clue. Either your memory has to be very sharp, means you have to remember. That means this is called photographic memory. Photographic memory, you remember things just like a photograph. You don't remember them by knowing the words. You remember them like a picture. Huh? Can you manage? Because if you don't manage when it is going to be conrotation and when it is going to be this rotation, you are not going to get your right answer. If con becomes this, you get a different answer. But con and this depends on what? Depends on whether the reaction is thermal or photochemical, and also whether the number of pi bond is odd or even. So all these factors are there. So there are too many factors. Again, I am giving you only one letter, a three-letter word, and that will make everything simple. This whole chart will come in that three letter. Whole chart will come here. Anybody who know that three letter? Anybody who knows it? Three letter. What is that three letter? Three letter word. Anybody? Hello? I'm giving you the final answer. Anybody who know it or not? Just come on. Come on. We have to finish it quickly. Nobody? Busy?
No, sir.
You know. Arukune ase sabana dekisu arukune. Both ase, but not they are not there in the picture. It is a very simple word. Just remember this. What is this? These three letters. T stands for thermal. O stands for odd. That means odd number of pi bond. Number of pi bond, not bilateral. Pi bond. And D is this rotator. That means when the reaction is thermal, taking place with odd number of pi bond, the rotation has to be this rotator. And as I am giving here extra, S is symmetric. That means the orbital is symmetric. The HOMO is symmetric for that system. That means if I have, suppose I have got now this system. I carry out the reaction under thermal condition. So what should be the rotation? Tell me. Rotation of the terminal bond, terminal orbital. Correct. Your answer is clear here.
This rotator.
This rotatory.
This, I write here this from this one. Now you check. check this. Check this chart. Check the chart here. What is this one? Odd, no? So this is odd. This is odd. Odd number of electrons. Sorry, odd number of pi bond. Reaction is thermal, and if it is thermal, this HOMO becomes symmetric, and it is disrotated. So you have to remember only one of them. Rest will come automatic. How automatic? Just see. If you change any one, suppose the condition becomes photochemical. So PO, if it becomes photochemical and it remains odd, this D will not remain D, this becomes C, conrotation. Rotation will change and S will become antisymmetric. Symmetric will become antisymmetric. But this S is not very much important now, because just to remember what is your HOMO of that under that condition, symmetric or antisymmetric. This becomes conrotation, POC. Now you check odd number, just see, this is odd number. Condition is photochemical. Oh, it's giving warning, 10 minutes more. Just see photochemical, and it will be antisymmetric, so this will be rotation, will be conrotation. So for this reaction, for this reactant, if the reaction is photochemical, the rotation has to be con, not this. Again, change to from, say, let us make it thermal, let it remain as it is. Any one you change. Suppose you change odd to even. So this will change to this will change to con. So thermal, even number of the pi bond, this will become conrotation. So let us take one even example. So this is even, this even number of pi bond. So this becomes what it is. Thermal. So it is thermal. So what will be the rotation? Rotation has to be what?
Conrotatory.
Conrotation. That's all. And but if you do it again photochemical, so the rotation has to be this rotation. If you change any one, this will change to con will change to this. Done? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So that's all.
Yes, sir.
That is, so everything that you get here, everything that you are getting here in this big chart is just present here, top. And this S I am giving here, S is just for symmetric. That means terminal lobe is symmetric or antisymmetric. When it is thermal, it is odd number of pi bond, the rotation has to be this rotation. If you change any one, this will change to con. If you change two, suppose it is thermal now, photochemical, this one also even number. So what it should be, con or this? Con or this?
Con.
How can it be con? Because you have made two changes. No, thermal has become photochemical and odd has become even. So it remains this. For one change. Suppose thermal you change to photochemical, this becomes con. You change odd to even, again that con becomes this. So it is coming to this. So it is this one which is, so this is the last part, thoughts. So you have to remember simply this this sentence, that this three letter POD. Everything is here. All the whole chart is here. What is next? So this is what is the gist that I have told you now, just now. Let us see. Ring closing. So this is the what happens. Terminal lobes, when it is ground state, it is gone. Just see. Just ground state antisymmetric, this will be con. The rotation has to, the rotation has to be con. What it is, you just get it from here, TOD. This is what ground state 4n system. 4n system is what? It is even. So this has become even. And if it is thermal, condition has to be given. This is thermal condition. Thermal condition. So this is thermal. So this D will become con. So this is con rotation. Con rotation, and the con rotation is same rotation this side and this side. When you do it, this lobe comes here. This lobe comes here. So there is bonding, in phase bonding. And for it is, this is odd system, right? And this is actually thermal. So what it is, it has to be, this is TOD. Just remember TOD system. TOD is, it is odd. So it is also thermal and odd. So it has to be this rotation. You see this rotation. And this means what? You have to come this way. So both the bonding is taking place, same phase coming. Ring opening. If I see ring opening, then what happens? In the ring opening, reverse things has to happen because they are reversible. You see, sorry, I'll change this sign also. This is not correct. We have to give the reversible sign. Reversible sign. Ring opening. So the pi system, it is even system. It is an even. Pi system is even, not odd, because we have to. What we are talking odd, even, it is that of the open chain system, open chain dying. So open chain dying after closing gives you this system. One bond is left, other bond is not there, and this methyl group is both are C's. So it is both of them are down. So this is ground state. So what is the bonding here? Bonding will be like this because the bond has formed. The two lobes has to be like this. So what should be the rotation? Rotation has to be con. So if it is con, this way it will rotate. So the one will go up here, and this will come down. So this blue sign will come here, and that has become homo. Homo is antisymmetric for this system, for pi, and under thermal condition is homo is antisymmetric. So we are getting back homo. So we should get back the homo, and that is equivalent to this one. So our product will be, you see this geometry. If we have this C's here, both are in the same side, our product will be this one. Just see. If I come here, oh no, okay. Now we can explain this. What was very confusing earlier, now we can very easily explain it. Let us see now. Here, this is a 3 electron. Just see. It is better to draw your molecule properly. Now, if you are doing it thermal condition, what is the number of pi bond is odd, right? So what rule will apply? TOD. So it is, the reaction is thermal, it is odd. So the rotation has to be what? This rotation. So we have to write here this. Now what is, now you give an imaginary line here, imaginary line. This means what? I have to go this way and I have to go this way. So if I go this way, what is the product? Product is going to be this one. This is the product. When I do like this, just like this methyl, where it is going? It is going up. Huh? And what will happen to this when I rotate it like this? What is this methyl? This methyl is also going up. Yes or no? When it is going up means what? It is becoming cis. It's becoming cis. So our product is cis here. Just see, we have written here cis. But if you do it photochemical, it is odd, but we have made it photochemical. Once it is photochemical means what? This will become con. So this is con. Once it is con means what? Okay, let me just rub this all. Oh, sorry. Hmm. Con means what? So now if it is photochemical, so rotation has to be con. If it is con, both will be same side rotation. So our product is going to be what? So what is happening if I rotate it like this? What happened to this methyl? Methyl will go up. Yes or no?